I'm Lee Feinberg. I'm the Chief Large Optics System Engineer at Goddard Space Flight Center and also the Optical Telescope Element Manager for the James Webb Space Telescope. I wake up every morning worrying about getting the telescope built for the James Webb Space Telescope. That's my primary focus. And that means everything from making sure that we're continuing to make technical progress on all the hardware, as well as planning for the future work for the telescope, including the testing of the telescope and the assembly of the telescope. Working with all the contractors and all the different teams that are supporting all of those different pieces of building the telescope. And I also developed technology, optical technologies for space applications. I was actually sort of one of the few people that was benefited from one of the biggest tragedies or mistakes that's ever been made on a space telescope, which is when the Hubble Space Telescope had the spherical aberration, NASA hired me as one of the people who was going to help on fixing the optical system, and was fortunate to work on the first Hubble servicing mission on the COSTAR and WFPIC-2 instruments, and then was the instrument manager on the second repair mission or servicing mission for Hubble, which was the STIS instrument. And so that's sort of how I got into the sort of space optics arena. It was a very significant problem, and if you remember, this was sort of at a time when NASA was recovering from what happened with Challenger and other things, and so it was a really difficult time for NASA. In some ways, it sort of parallels what we're going through now at NASA with all the changes going on in terms of how important it was at the time for us to be successful on that mission. And there was a lot of pressure. We actually did the whole Hubble servicing mission in about 3 years, from understanding we had spherical aberration to building instruments, building optics that would correct it, making sure that we got it right. We couldn't afford to get it wrong. It was really the first repair mission, so the astronauts were intensively studying how to service Hubble correctly, and everything went like clockwork. And I would say that was it was a great feeling to when we got it fixed, and we saw when the first images came down. That was just that was really one of the highlight of my career. Was seeing those first images come down on the repaired Hubble. If you looked at how much the Hubble Space Telescope cost, particularly if you put it in today's dollars, and you look at what James Webb is going to be able to do, these are the cost is really comparable in the inflated cost of Hubble. And James Webb is an ambitious mission for NASA, but the science is so incredibly powerful. It's literally 100 times more sensitive in most of the wavelength band. Some of the wavelength band, it's even more than that, more sensitive than a factor of 100. And the science it can do is so astounding, and it will bring back the kinds of discoveries that we got with Hubble. There's a number of lessons learned that came out of Hubble that we've been applying in terms of making sure we're very open about information, and that the other big thing that we're doing, I think, on James Webb that gives me a lot of confidence that everything's going to work is we're doing a lot of cross-checks. And sometimes with cross-checks, they don't necessarily have to be the same precision of the original measurement, because maybe it's too expensive to do that. But you can do a cross-check that's of a little looser tolerance, but is a lot less expensive test that gives you high confidence that what you've made doesn't have a major blunder in it. And we keep track of these cross-checks on our program, and we feel very confident that we're doing a number of these such that when we launch and get in orbit, that the probability of a blunder, a large blunder anyway, is very, very small. Also keep in mind James Webb is an active telescope in the sense that the primary mirror each mirror has degrees of freedom, and you can actually shape the primary mirror so if we actually did have the same type of problem they had on the Hubble Space Telescope, we actually could correct it fairly well with our active controls. The other piece of course, is the non-optical pieces like the deployments, and there, really the keys are putting in the levels of redundancy that you can and doing as much testing that simulates the space environment as you can, and that's really the philosophy. So we had to make almost visible wavelength mirrors that were a factor 10 lighter areal density than the Hubble primary mirror, and they had to operate at 50 degrees Kelvin. And that was a major challenge. Another technology that we're really proud of is the wavefront sensing and control. The trick was being able to align the mirrors in space, but not requiring a whole dedicated instrument to doing wavefront sensing and control. And the reason we couldn't afford to have a dedicated instrument was because of the mass that would entail and the complexity to the system. And so by making a few little modifications to the NIRCam instrument, the key science instrument in James Webb, we're actually able to take defocused images and use some grisms to align the telescope in space. And one of the things we had to do on the ground was build a scaled telescope testbed. Looks like James Webb, but is only a 1 meter diameter, not 6.5 meters. And we went through all of the algorithms initially to demonstrate that it was feasible, and then all of the ones we've developed for the flight application we've used in sort of a high performance mode and demonstrated that they work. So again, wavefront sensing and control now is behind us, another major achievement. And then the third one was the lightweight composite material that we needed that had to operate at 50 degrees Kelvin and be very stable. And that one, again, we were able to demonstrate that we can make a very stable composite material that's very lightweight. And we're in the middle now of manufacturing the backplane that will hold all of our mirrors that's made out of this material. In order to develop those technologies, we had to invent other technologies. And I'll give you an example. We had to invent a new type of wavefront sensing or wavefront sensing measuring device. It was called a scanning shack Hartmann for measuring our mirrors at intermediate steps as we ground them. And it turns out that the company that developed that scanning shack Hartmann for James Webb's purpose was then able to take that technology and apply it to the measurement of human eyes. And actually now that company got bought by a medical company, and they're going to be making these sensors for the purposes of measuring eyes for eye surgery, like LASIK eye surgery and other eye applications. So that's a good example of the kinds of spin-offs that we're getting from James Webb. And there are other spin-offs in terms of some of the manufacturing processes, et cetera, that are also going to have wind up potentially in your home. Yeah, it's been a technologically ambitious project, but we're developing technologies and infrastructures that are going to serve humanity for a long time.